Greetings class and welcome to the last of our lecture here for this unit. And in this unit we're going to go over what I call exceptions to the rules. So we've laid down some very um, layers of rules to how ocean circulation occurs. Um, and we've paid particular attention here as to the many weather atmospheric and ocean circulation patterns that set up ways for the two layers of the ocean to mix, and some of them setting up long-term phenomenon such as the Equatorial Pacific and the Western Warm Pool, and this is pretty much the norm in all oceans where you have sort of a pattern that's normal or long-term and persistent, but then we have these events and patterns that happen kind of on top of these, that shift conditions. We're going to talk about some of those today, and the real showcase for this lecture is El Nino. It's one of the largest. It's got some of the biggest consequences, and it's one of the more well understood ones. We've studied this quite a lot. Okay, so El Nino has to do with a change in the way that the Equatorial Pacific is set up. And so to review, we have these long-term zonal winds that come across the Equatorial Pacific. They set up a warm, humid atmosphere on the eastern side, the western side of the ocean basin, which is Southeast Asia. And this cool, drier system on the eastern boundary of the ocean basin, and this is Central and Latin America. And we set up this Walker cell, and what it does is pile up all the warm water over here in what we call the Western Warm Pool, right? Raises the sea surface temperature by piling it up over there, lowers the thermocline, deepens the thermocline, and warms the ocean as a whole in the surface over here. Has the opposite effect, depresses sea level, raises the thermocline, and keeps this water cooler over here because we get an upwelling, right? This along here we get this divergence of water along the equator. The divergence causes upwelling, and when the upwelling breaks through the thermocline, we bring up nutrients and cause all this productivity. So if we set that aside as the normal conditions, during an El Nino event, which occurs approximately every 3 to 7 years. An event happens, and many people will disagree on what the main cause of these are, or maybe there's several. But there's definitely one event that oceanographers agree on called a western windburst, which is when atmospheric conditions off here on the continent release winds, some persistent and strong winds coming off the continent, something that shrinks the Walker cell, or I should say weakens the Walker cell. So it pushes back on these zonal winds, decreases these zonal winds, and shrinks the Walker cell so that it's now not quite as strong. The entire phenomena that sets up these dynamics for the Pacific Ocean are not as strong. So what are the consequences for that? We know that these strong winds cause this strong divergence as you get away from the equator, right, away from here. And we know that strong if we weaken those winds, if we weaken these winds, then we're going to weaken this divergence, okay, if not cancel it out in some areas altogether. If we weaken this divergence away from the equator, if we're looking at a cross section, then we also weaken this upwelling, right? We get that upwelling. So here's another look at the normal conditions, right? So let's look at the consequences again. If we weaken these winds, then these arrows are going to shrink, right? The upwelling event is going to shrink because we've decreased the amount of divergence along there. If we weaken these arrows, then they're not penetrating as deep into the ocean. But also if we weaken these winds, if you remember the winds pushing continually this way over here are what are piling all this warm water up over here. So if we weaken these winds, then we also get a shift of the Western Warm Pool. Okay, we all of a sudden just let go of this pile of water, and it sloshes eastward. And so the effects of those are manyfold. Okay, the heightened sea surface over here is reduced, is let go. The deeper thermocline is reduced, and the thermocline just levels off, and sea surface level raises over here, and this warm water just shifts this way. But the other effect is smaller arrows, deeper leveled off thermocline, so these arrows that represent the upwelling are no longer breaking through the thermocline into the deep water, and so what we've done is effectively canceled out this upwelling of nutrients and carbon and oxygen rich water that washes up, causing the equatorial upwelling productivity events. All right, so you can think ahead. What are the consequences of that? What does primary productivity in the ocean do, and what happens if we cancel out a big portion of that? So here's a 3D depiction of the normal conditions, right? Continual persistent winds piling up the warm water over here, deepening the thermocline, raising sea level over here, causing this upwelling event, this upwelling of cold, nutrient-rich water, as we go towards the eastern boundary of the ocean basin. We get a release of these winds, so the winds are much smaller. The thermocline levels off. Sea level goes down over here and goes up over here. We reduce the amount of upwelling, if not cancel it out altogether. And then this warm, humid atmospheric climate that happens along the western boundary of the ocean basin shifts eastward, and changes the entire atmospheric conditions from here to over here. Here's a model of modeled pictures of actual data from the 1997-98 El Nino event, and you see that during January 1997, at the beginning of an El Nino event, we still had normal conditions. So this is the Pacific Ocean. Right along here is the equator. You can see up here is North America, Alaska, and into Europe. And we had a deep thermocline, the western warm pool, all built up over towards the western side of the ocean basin. Shallow thermocline, cooler waters from all this cold water upwelling on this side. By 6 months later, after the El Nino event began, we see the thermocline has leveled off dramatically. Sea surface height is down here, sea surface height is up over here, and we see that the warm water pool is shifting eastward. If we go another 6 months or so into the future, in November of 97, we see now that, so it's not quite as straightforward. It doesn't all just level off and equilibrate, but it's more like letting go of a big pile of water in your bathtub. It actually sloshes before it equilibrates. So you get the warm pool has completely shifted, almost completely shifted, all the way to the east, and for a short time at least, the thermocline has deepened over here. It's much warmer over here. The thermocline has shallowed a little bit over here. And you see that by March 1998, which is a full year after the event began, or more, it's still the ocean basin has still not started to shift back to normal conditions. Right? It's still warm over here. The thermocline is much more level than normal conditions, and there's still all this warm water gathered over on the east side. So what are the consequences? You guys should be thinking ahead. So I've changed all these atmospheric conditions. I've changed all these ocean environmental conditions, and we know what some of the consequences are for the normal. So we know what the effects are for the normal conditions. What are the consequences for when we shift these? Part of it has to do with temperature in and of itself, right? So if this is the average temperature of the sea surface ocean across that year of an El Nino event, the 97-98 El Nino event, you see that the average temperatures were much warmer off to the east here. But it doesn't just travel along the equator, it sloshes, like we said, just like in your bathtub. It actually travels and splashes and travels up and down the coast, making all these warm sea surface temperatures, much warmer than usual. And so the effect when you change the environmental conditions, especially on something as sensitive as a coral, is you can have anywhere from 75 to 95% die-off of some of these species. Coral need very specific temperatures, and they're sensitive to changes in temperature and other environmental conditions. But when you decrease all this upwelling of the nutrients, and you're effectively canceling out the large pulses of primary productivity that occur with the phytoplankton, and when the phytoplankton don't grow, the zooplankton don't eat them. Zooplankton like the protozoa and the copepods, and then the organisms that eat them cannot continue to thrive as well, and they die off or they don't grow as well that year, and they can trickle all the way up to the small and economically important organisms like anchovies. You can have as big as a 9 million metric ton decrease in the anchovy catch. I think that was in the 1980, during the 1982-83 El Nino event. Um, the things that depend on small fishes and these other organisms for their prey, such as seabirds, they die off as well because they have a large shortage of food. So during one of these El Nino events, we went from having 27 million seabird population to about 1.8 million. I mean, that's an incredible die-off. Anything that eats these guys or these guys and is dependent on the food chain below them, we have die-offs. And this is specifically large impact to some of the bigger mammals and top predators because there are fewer of them and they're not as prolific. They don't produce thousands of young, and they don't have generation times. They don't reproduce within a day. They take a full year or more to reproduce, and so we have large die-offs of some of these larger mammals like seals, sea lions, dolphins, whales, all these things that depend on these things. Besides for the direct biological ramifications, we have we have changes in the environments or the territories that species end up moving to or breeding in, because now we've shifted and turned this normally cool water environment to a warm water environment. So you have species that usually are out to sea traveling into the coast and up and down the coast, and species that are usually in that cooler environment traveling further and further away to environments where that are more natural for them. Beyond the biological ramifications, we have a lot of physical ones that are sort of obvious when you think about the normal conditions. So we had depressed sea level, so a low sea level, and cool and dry conditions on the eastern boundary along Central and Latin America. But when we shift all this moist water and the entire sea surface towards the east, we get a rise in sea level, which will affect all the organisms that grow along the coast, but also the humidity and the rise in sea level bring massive rains and massive flooding to the coastal areas. And the opposite effect happens on the western boundary of the ocean for certain times of this event, right? So we used to have high sea level and warm, humid atmosphere, but now we have a dry and hot atmosphere and lowered sea level. So we get severe droughts, and along with droughts, we get a lot of fires on the continents in Southeast Asia. So another, whoops, that's supposed to be P. There we go. Change that to Pacific decadal oscillation. There are a couple of other patterns and events that are a little bit more predictable, but probably less understood than the El Nino. Like, we understand exactly the mechanisms and what's going on in the El Nino, but there are these long-term sort of negative positive phase circulating changes in sea surface temperature and some of the other environmental parameters that happen, and they're difficult to understand, mostly because they happen on very long time scales. And one of them is this Pacific decadal oscillation, where the temperatures oscillate on the order of about 10 years or so, 10 to 20 years, and that's why we call them decadal. And it's a cycle where there's this negative and positive warm phase in the Pacific Ocean. So if we forget about El Nino and we just think about the natural sea surface temperatures in the northern Pacific, there's this long phase where the northern part of the Pacific Ocean is cooler than average, and then it circulates and cycles within 10 to 20 years or so to where the northern parts of the Pacific Ocean are warmer than average, and it cycles back and forth between these two again on about every 10 to 20 years or so, and so we call that an oscillation. There's another one, a similar thing that occurs in the Atlantic, the multi-decadal oscillation, and this occurs about every 20 or more years, so it's a longer term, and we just have this warmer phase and cooler phase. You see, between July and 2005 to March 2009 is where we had a switch. And so it's a similar thing. It's just a long-term switch in the average temperature of the ocean. And here we could see here's the PDO. We have a warm phase, cold phase, warm phase, cold phase. Same thing with the AMO, warm phase, cold phase, warm phase, cold phase, warm phase. And these are just extra patterns, events that happen on top of the circulation that we've been talking about so far. See you next lesson, guys.